A profound pattern hides within our history books. The story of human invention is not always written in fertile valleys or bustling ports. It is carved deep into the rock of the world's most difficult places. Some of our greatest leaps in technology, from mastering metal to harnessing steam, emerged not where life was easy, but where it was a relentless struggle underground. This video will uncover the hidden forces that transformed harsh mining regions into the world's first innovation hubs. We will explore why these remote, mineral-rich zones became crucibles for progress, solving puzzles that others never had to face. You will learn a fundamental truth about how human ingenuity is sparked, a principle that goes far beyond the simple idea of necessity. What strange alchemy turned rock and darkness into engines of light? And why did the very hardship of these places accelerate invention rather than stifle it? By the end, you will see the blueprint for how true breakthroughs are born under pressure. What forgotten place in your own world might be hiding a similar potential for transformation? These places are not just names on a map. They are the original laboratories of human progress. To understand their power, we must first walk the ground of a few key locations, each a chapter in this global story. High in the rugged borderlands between what is now Germany and the Czech Republic, the Erzgebirge, or Ore Mountains, rise from the earth. For centuries, this was a landscape of dense forest and harsh winters, seemingly offering little. Then, in the 12th century, prospectors discovered veins of silver so rich they called the main settlement Freiburg, the Free Mountain. This was not surface wealth. The silver was locked deep within the rock, demanding new ways to dig, to drain, and to survive. 1,000 years earlier and far to the south, the fate of an entire civilization was being forged underground. The Laurion silver mines, a sprawling network of tunnels and shafts just south of Athens, provided the immense wealth that built the Athenian navy, the very fleet that saved Greece during the Persian Wars. This silver financed democracy itself, but it was extracted through back-breaking labor in stifling, dangerous depths, pushing the limits of ancient engineering. Across the sea, the island of Cyprus was so famed for its copper that the metal itself took the island's name. For millennia, its mines supplied the essential ingredient for the Bronze Age, an era defined by this revolutionary alloy. And in Britain's southwestern tip, the rocky peninsula of Cornwall held Europe's most significant deposits of tin, the other vital component of bronze. Securing these distant, mineral-rich lands was a driving force of ancient trade and conflict. Even something as fundamental as salt, essential for preserving food, spurred innovation in its extraction. At Hallstatt in the Austrian Alps, a community thrived for over 3,000 years around salt mining, developing sophisticated timber engineering to reach the precious deposits deep within the mountain. Each of these sites, from the silver mountains of Germany to the salt halls of Austria, shares a crucial common thread. We are looking at the world before industrialization, before dynamite and diesel engines. This was mining at its most physically demanding. Every inch of progress was won by muscle, sweat, and sheer stubbornness against an unyielding earth. The rock was hard, the air was thin or foul, and water was a constant, flooding enemy. It was within this crucible of extraordinary difficulty that the pattern first becomes visible. Why did these specific spots, defined by their hardship, become the unexpected birthplaces of technological leaps that would reshape the world far beyond their tunnels? The answer lies not in the minerals they took from the ground, but in the relentless problems they were forced to solve. The difference between a difficult task and an urgent crisis is the spark of invention. For a farmer, a poor harvest is a slow-moving disaster, a problem measured in seasons. But for a miner deep underground, a sudden flood is not a future worry. It is a wall of water rushing toward you in the dark, right now. The very nature of mining created a world of immediate, unyielding problems that demanded immediate, tangible solutions. There was no time for abstract theory or gradual experimentation. The rock does not negotiate. The air, when it grows still and thick with dust, becomes a silent, invisible threat. Every single day presented a clear, physical puzzle with life or dear stakes. How do you keep a tunnel from collapsing on the workers inside? How do you lift a ton of ore from a depth of 500 feet using only human strength? Most critically, how do you keep the labyrinth of tunnels from filling with water, or the air from becoming so foul it extinguishes your lamps and your life? These were not intellectual exercises. They were brutal, practical obstacles standing directly between a community and its survival, between an investor and his fortune. This created a feedback loop of incredible intensity. A problem would arise like a chamber flooding. The miners would attempt a solution, perhaps a simple hand-operated pump. When that proved insufficient, they would improve it or invent something entirely new, like a series of waterwheels connected to piston pumps. The success or failure of that invention was measured in the most concrete terms possible. Did the water level drop? Did the mine stay open? Profit and life itself were the ultimate judges of every idea. This stands in stark contrast to the challenges of agriculture. A farmer might wish for a better plow, but a bad design means a slightly smaller yield at the end of the year. A miner's flawed support beam or inadequate ventilation system meant catastrophe by the end of the hour. This relentless pressure, this daily confrontation with the uncompromising laws of physics, made mining regions unparalleled problem-solving engines. The solutions they forged were not born from leisurely contemplation, but from the urgent, grinding necessity of the moment. But pressure alone does not create a revolution. It forges the need, but something else must gather to meet that need. Think of a single, desperate miner staring at a flooded shaft. His determination is immense, but his tools are limited. Now picture an entire valley dedicated to that single, monumental task. This is the second crucial ingredient. The immense value locked in the earth acted like a powerful magnet, pulling every essential element for innovation into one concentrated, hyper-focused space. First, it drew the people. A major mining operation was not just a hole in the ground. It was a complex, living organism that required a vast array of specialized skills. You needed the miners themselves, of course, the brave souls who ventured into the dark, but you also needed the engineers to design the timber supports that kept the tunnels from collapsing. You needed the master smelters who understood the alchemy of turning raw, rocky ore into gleaming, pure metal. You needed carpenters to build the massive water wheels, blacksmiths to forge the durable tools, and cartwrights to maintain the wagons that carried the wealth to the surface. This created an unprecedented concentration of talent. For the first time in many regions, a master pump designer from one town could walk down a muddy path and have a conversation with a master metallurgist from another. They were not separated by miles of farmland, each working in isolation on different problems. They were neighbors united by a single, overwhelming challenge. How do we get more silver out of this mountain? Their ideas collided and combined in the taverns, at the smelting works, and by the mine head. A solution devised for a ventilation problem might spark an idea for a more efficient ore crushing mechanism. This constant, informal exchange of knowledge in a dense community of practitioners accelerated learning at a rate impossible in scattered, agrarian societies. Second, and just as importantly, this concentration applied to capital. Mining was astronomically expensive. Digging deep shafts, building drainage adits that ran for miles, constructing elaborate pumping systems. These projects required investments that could bankrupt kings. But the potential payoff was equally staggering. A single rich vein could yield a fortune. This high-risk, high-reward equation created a powerful incentive for investors, often wealthy merchants or nobles, to fund experimental technology. If investing 100 gold pieces in a new type of lifting engine could prevent the collapse of a mine yielding 1,000 gold pieces a month, the gamble made perfect sense. The value of the output justified the risk of innovation. This is why we see some of the earliest and most sophisticated applications of water power not in peaceful grain mills, but in the frantic effort to drain the silver mines of the Erzgebirge. It is why complex systems of gears, chains, and buckets were developed in Cornwall to haul tin from ever greater depths. The mine became a laboratory where capital, expertise, and desperate need converged, creating a perfect storm for technological trial and error. The next great leap, however, would not come from improving muscle or even water. It would require taming a far more powerful and dangerous force. The rock was only the beginning of the challenge. Pulling raw ore from the earth was a monumental feat of engineering, but what emerged was not treasure. It was a dirty, heavy, and often worthless-looking stone. The true magic, the transformation of this crude material into something that could build cities or forge empires, happened above ground in a storm of fire and ingenuity. This was the metallurgical imperative, a second wave of innovation forced upon these regions. Simply having the ore meant nothing. You had to unlock its secret. Every mining region, therefore, became a center for advanced materials science, pushing the boundaries of chemistry and heat long before those were formal fields of study. The process of smelting is a kind of alchemy. It requires extracting the pure metal from the rocky ore that encases it, usually through intense heat. Early furnaces were simple pits or clay ovens, but as miners dug deeper, the ores they found were often more complex, more stubbornly bonded to the rock. To get a better yield, you needed a hotter, more controlled fire. This drove constant experimentation with furnace design, with the types of charcoal used, and with the way air was blasted into the fire to raise the temperature. In Cyprus, for instance, the drive to produce more copper led to the development of specialized furnaces and slag tapping techniques that made the process vastly more efficient. But the story grows even more fascinating when a single metal was not enough. Consider bronze, the alloy that defined an entire age. Bronze is not a natural metal you dig up. It is an invention, a deliberate recipe combining two softer metals, copper and tin, to create something harder and more durable than either. Here, the mining imperative created a puzzle of global scale. Copper deposits and tin deposits are rarely found in the same place. The rich copper mines of Cyprus were thousands of miles from the vital tin mines of Cornwall. This geographical separation sparked one of history's first long-distance, high-stakes trade networks. Securing this tin was not a matter of luxury. It was a strategic necessity for any civilization wanting advanced tools and weapons. The need to combine these geographically separate resources drove advances in shipping, navigation, and international commerce. It forced cultures to interact, trade, and share knowledge on a scale previously unseen. The metallurgical challenge did not stop at mixing metals. The ultimate test came with iron. Iron ore is common, but transforming it into usable metal is notoriously difficult. It requires far higher temperatures than copper or tin, and the process is delicate. Early iron was often brittle, of poor quality, but the communities that had spent generations mastering fire and chemistry around their mines were uniquely positioned to crack this code. Through relentless trial and error in their forges, they developed techniques like repeated heating and hammering to drive out impurities, creating a much stronger product. This was not a discovery made in a royal court. It was forged in the practical, profit-driven workshops that surrounded mining districts, where the penalty for failure was a useless batch of metal and a significant financial loss. From the alloying of bronze to the refining of iron, the mine was the mother of the metallurgist. the relentless demand to turn heavy, worthless rock into lightweight, valuable ingots created a perpetual innovation cycle right at the smelting site, turning these remote regions into the world's first advanced industrial laboratories. The furnace and the forge demanded a fire that never slept, but the deepest challenge lay in moving mountains of water. Every ounce of metal extracted from the earth came with a hidden, liquid cost. As miners chased veins deeper into the bedrock, they were pursued by a relentless enemy, groundwater. It seeped through cracks, gathered in pools, and without warning could burst into a torrent that drowned tunnels and dreams in an instant. To mine deeper was to wage a perpetual war against the ocean hidden within the stone. This battle for dryness became the single greatest driver of energy innovation the world had yet seen. The early solutions were brutally simple, a testament to sheer human endurance. Teams of workers would form bucket brigades, passing leather containers hand over hand up long wooden ladders from the flooded depths. Animals, donkeys or horses, trudged in endless circles, turning capstans to wind rope and lift heavier loads. But these methods hit a physical limit quickly. The deeper the mine, the more energy was required just to lift the water out, and human and animal muscles simply could not produce enough continuous, reliable power. The mine demanded a force of nature to combat a force of nature. That force was water itself. Ingenious engineers began to harness the streams and rivers that flowed down the mountainsides, not for their content but for their motion. They constructed massive waterwheels, sometimes over 30 feet in diameter, made of stout timber. These were not the gentle wheels turning millstones for grain. These were industrial power plants. The flowing water would turn the wheel, and through a complex system of wooden rods, gears, and axles called a flatrod system, that rotary motion was converted into a powerful, vertical pumping action. A single great wheel could operate a bank of piston pumps, sucking water from deep underground and spewing it into drainage channels. In the Erzgebirge, they built entire cascades of these wheels, a symphony of wood and water working day and night to keep the silver veins accessible. The mine had become a university for mechanical engineering, teaching a generation how to capture, transmit, and apply power over long distances. Yet even the mighty waterwheel had its weakness. It was geographically trapped. You could only mine where a strong, reliable stream could be diverted to power your pumps. The richest veins, however, did not care about the location of rivers. The quest to unlock these trapped treasures would lead to the invention that changed everything. In the early 18th century, in the tin mining region of Cornwall, a metal worker named Thomas Newcomen faced this exact problem. The tin deposits were deep, the water was overwhelming, and there were no nearby streams powerful enough to drive the necessary pumps. Newcomen's brilliant, clanking solution was the atmospheric steam engine. It was a monstrous machine, a giant brass cylinder with a piston, powered not by flowing water, but by creating a vacuum with condensed steam. With each great sigh of the engine, it pulled on a massive beam, which in turn worked a pump deep in the mine shaft. It was inefficient, it gulped coal, and it shook the ground, but it worked. It could be built right at the mine head, anywhere. For the first time, humanity had decoupled heavy industry from the direct whims of geography. The Newcomen engine and its more efficient successors perfected by James Watt were not born in academic halls. They were forged in the direct, desperate need to keep the Cornish tin mines dry. The steam engine was a child of the mine, a direct answer to its most fundamental question. That same technology, refined and scaled, would soon leave the mineshaft behind to power factories, locomotives, and ships, igniting the Industrial Revolution. The relentless energy hunger of the deep mine had forced the creation of the very engine that would power the modern world. The steam engine was a monumental answer, but it was born from a much older, more fundamental question. How do you even reach the ore in the first place? The rock itself was the original teacher, and its lessons were unforgiving. The specific geology of a mining region acted as a powerful forcing function, a relentless instructor that dictated the exact curriculum of innovation a community had to master. Not all mining was created equal, and the nature of the deposit directly shaped the technological path that followed. Compare two very different scenarios. Imagine a riverbed where over millennia, flowing water has worn down rock containing gold, depositing the precious flecks in sandy sediment along its banks. This is alluvial mining. The work is backbreaking, involving sifting through tons of gravel and sand, but the technical challenges are relatively straightforward. You need shovels, sluice boxes, and a lot of patient labor. The problems are above ground in the organization of work and water flow. Now picture the opposite. A slender, vertical vein of silver quartz, a thread of wealth plunging hundreds of feet down into the heart of a mountain of granite. This is deep vein, hard rock mining. Here, the ore is not a gift scattered by a river. It is a secret locked in a stone vault, and the mountain does not want to give it up. To follow that vein, you must become a master of underground architecture. The empty space you create is inherently unstable. The weight of the world above presses down, wanting to collapse your tunnels. This single, brutal fact of physics forced the invention of sophisticated timber framing, known as square-set timbering. It was like building a three-dimensional wooden skeleton inside the mountain, a self-supporting grid of massive beams that could hold up the ceiling while miners carefully extracted the ore from within the honeycomb of wood. This was not simple carpentry. It was structural engineering in its most urgent form, where a design flaw meant a catastrophic cave-in, but timbering only solved the problem of space. You still had to break the rock. Following a deep vein meant drilling into the hardest granite, inch by agonizing inch. The old method of heating the rock with fire and then dashing it with cold water to make it crack was slow and unpredictable in these deep, airless environments. The need for a more reliable way to fracture stubborn rock led directly to the development of advanced drilling techniques and ultimately to blasting. Initially, miners used crude tools and sheer muscle power to hammer metal drills into the face of the rock. Later, they mechanized this process with piston-driven drills powered by the very steam engines that pumped out the water. And to break the rock free, they needed a controlled force. This led to the adoption of gunpowder and later dynamite for mining purposes. The dangerous work of setting charges in confined spaces drove improvements in safety fuses, detonation methods, and the precise science of how to fracture rock without bringing the entire tunnel down on your head. So, while a surface miner might innovate a better sieve, the hard rock miner was forced to become an expert in subterranean construction, mechanical drilling, and controlled explosives. This pattern holds true across history. The most technologically prolific mining regions were very often those blessed with the most difficult, most deeply buried deposits. A rich, easy surface deposit could be exhausted quickly, leading to a short boom and then abandonment. But a challenging, deep-seated ore body presented a continuous, escalating series of puzzles. Abandonment was always the easiest option. The only alternative was ingenuity. The mountain, in its stubborn refusal, became the greatest teacher. It did not simply give up its treasure. It demanded payment in the form of new knowledge, forcing generations of miners and engineers to learn the language of pressure, fracture, and support. This harsh dialogue between human need and geological reality is where we see the blueprint for progress written in stone. The next layer of this story, however, moves from the physical challenges of the rock to the human systems that grew around them. How did these intense, remote communities organize themselves to sustain such a relentless enterprise? The solutions forged in darkness did not stay trapped underground. They flowed outward, reshaping the very landscape above, building the bones of the modern world. The most immediate and visible spillover was transportation. A mine is a point of intense production, but its wealth is useless if it cannot reach a smelter, a port, or a market. Moving tons of dense, bulky ore over the rugged terrain typical of mining regions was a logistical nightmare that sparked revolutions in how we move things. Before engines, gravity was the primary ally. Miners built wooden tramways, simple tracks with flanged wheels, to guide horse-drawn wagons loaded with ore down from the mountain slopes more efficiently. These wooden rails evolved into iron ones, and the need for a more powerful, reliable pull than horses on steep grades directly fueled the development of the steam locomotive. The first true railways were not built for passengers or general freight. They were industrial arteries like the Stockton and Darlington line in England, designed specifically to haul coal from mines to rivers. The railway was born from the mine's appetite for movement. Similarly, where water transport was possible, the demand to ship bulk minerals led to the cutting of sophisticated canal networks. In Cornwall, entire ports were engineered and deepened to handle the constant flow of tin ingots onto waiting ships. These were not gentle country canals for leisurely trade. They were high-capacity, engineered waterways built for economic survival. Once established, this new infrastructure did something extraordinary. It unlocked the region. The railway built for ore could now carry farm produce to distant cities at unprecedented speed. The canal dug for copper shipments could now transport textiles, pottery, and people. The mining district, once a remote and difficult destination, became a connected hub, its transportation web boosting all forms of commerce and binding isolated communities into a larger economic whole. The mine's logistical problem had gifted the region a circulatory system. This transformation required a new way of seeing the land itself. You cannot drain a mountain, tunnel through it, or build a rail line across it without first understanding its hidden anatomy. The relentless practicality of mining drove a parallel revolution in measurement and representation, in the science of seeing what lies beneath. Surveying and mapmaking ceased to be abstract arts and became essential, precision tools for survival. To dig a drainage adit that would slope perfectly for miles to intercept groundwater, you needed incredibly accurate measurements of elevation and direction. A miscalculation meant years of wasted labor and a tunnel that missed its target entirely. This pressure gave rise to advanced surveying instruments and techniques. The theodolite for measuring angles was refined in these environments, but the most profound innovation was in cartography, the making of maps. Miners did not need maps of political borders or pretty landscapes. They needed three-dimensional blueprints of the underground, showing the twist and turn of every vein, the intersection of every tunnel, the depth of every shaft. They began creating detailed cross-sectional maps and geological plans, some of the earliest technical diagrams that attempted to visualize the invisible. This was not just drawing. It was a new language for describing the subsurface world, a language of layers, faults, and deposits. This meticulous, practical approach to mapping the Earth's crust laid the groundwork for modern geology and civil engineering. The same skills used to plot a mineral vein were later applied to planning roads, bridges, and aqueducts. The engineer who learned to stabilize a mine tunnel with complex timbering became the expert who could design the foundations for a cathedral or a fortress. The knowledge was directly transferable. The mine was a brutal but effective training ground, teaching generations how to read the land, challenge it, and reshape it with confidence. The infrastructure born of mineral wealth, from the rail tied to the topographic map, became a permanent gift to the surface world, a foundation upon which all future building would depend. Yet, for all this outward progress, a profound tension was growing within these innovative communities themselves. How did the relentless drive for efficiency and the immense value being created affect the people whose labor made it all possible? The social world of the mining camp became its own kind of experiment, one with lasting consequences. But innovation is not only about machines and maps. The true machinery of the mine was human, and organizing it required a revolution of its own. The immense scale and staggering risk of deep mining created problems that could not be solved by a better pump alone. They demanded new ways of thinking about money, ownership, and work itself. The financial challenge was absolute. Sinking a single deep shaft could take years and consume a fortune before a single ounce of silver was seen. No individual prospector, not even a wealthy landowner, could typically shoulder that burden alone. If the vein ran dry or a flood proved unstoppable, the loss was total. This perilous equation gave birth to some of the earliest forms of the joint stock company. The idea was brilliantly simple, yet radical. Instead of one person bearing all the risk, the cost of the venture was divided into shares. Many investors, from local merchants to distant nobles, could buy a piece of the action. Their potential profit was proportional to their investment, but crucially, their liability was limited to that same amount. If the mine failed, they lost their stake but not their entire fortune. This system pooled capital on an unprecedented scale, turning a risky gamble into a calculated investment. It was early venture capital, driven by the glittering promise of mineral wealth. The mine became a financial laboratory, experimenting with contracts, profit-sharing agreements, and insurance schemes to manage uncertainty. Managing the flow of money was only half the battle. You also had to manage an army. A large mine was one of the most complex human organizations of the pre-industrial world. It required a strict hierarchy and a division of labor far more specialized than a farming village. There were hewers who cut the ore, trammers who hauled it, carpenters who timbered the tunnels, smiths who sharpened tools, and engineers who oversaw the machinery. Coordinating these groups, ensuring they had the tools and materials they needed, and tracking their output was a monumental administrative task. This drove innovations in accounting and logistics. Mine managers developed detailed ledgers to track expenses for timber, iron, candles, and wages. They created inventory systems to manage supplies that might take weeks to arrive along fragile supply chains. The need to pay workers and suppliers on time and to account for the value of ore extracted fostered more sophisticated bookkeeping practices that would later become standard in all large businesses. The social structure within mining communities often reflected this organized, practical mindset. In places like the Erzgebirge, miners formed strong guild-like associations that provided mutual aid and established codes of conduct. These were not feudal arrangements based on land, but professional societies built around a shared, skilled trade. The relentless, coordinated effort required to challenge the mountain forged a unique social contract, one built on interdependence and the precise value of specialized labor. This was a quiet, profound shift. The mine was not just extracting metal, it was prototyping the very financial and organizational blueprints. The joint stock company, the specialized workforce, the detailed ledger, that would later power global trade and the corporation itself. The pressure of the deep earth had forced the invention of new social technology to match its physical machines. Yet this new world of capital and labor needed a memory. The brilliant, improvised solution to a cave in one tunnel could mean life or death for miners in another, miles away. But in an age before patents and engineering journals, how did a breakthrough survive its inventor? The answer lies not in a library but in a lodge. The miners formed their own republics of knowledge, bound by oath and necessity. Across Europe, from the Harz Mountains to Cornwall, powerful guilds and brotherhoods emerged. These were not simple trade unions. They were the world's first dedicated research and development communities, built around the most valuable currency of all, practical know-how. Membership was exclusive, often hereditary, guarded by strict initiation rites. An apprentice spent years not just swinging a pick, but learning the sacred geometry of timber framing, the subtle signs in rock that predicted a rich vein or an impending collapse. the alchemical recipes for refining stubborn ores. This knowledge was a closely held secret, a guild's competitive advantage. To reveal the details of a new pumping design to an outsider could be considered a betrayal. But within the Brotherhood, knowledge flowed freely and systematically. Experienced miners, the masters, were obligated to teach the next generation through a formal apprenticeship system. Techniques were not left to chance or vague memory. They were codified into rules of thumb, documented in detailed guild ordinances, and even celebrated in song and ritual. The annual Miners' Parade, with its specific symbols and costumes, was a walking textbook of their craft, a way of passing down identity and expertise in one powerful ceremony. This created a living chain of technical transmission that could stretch over centuries. A timbering method perfected in the silver mines of Saxony in the 1500s could, through the network of migrating master miners, find its way to the copper mines of Sweden a generation later. The guilds acted as a filter for innovation. When a miner stumbled upon a better way to set a charge or brace a shaft, that idea would be tested in the harsh laboratory of the mine. If it proved itself saving time, money, or lives, the guild would adopt it, standardize it, and teach it. Failed experiments were remembered as cautionary tales. This constant, collective vetting process accelerated progress in a way isolated tinkerers could never achieve. It meant that a breakthrough in one dark corner of the continent did not die there. It was captured, refined, and added to the growing body of mastercraft, ready to be deployed wherever the Brotherhood dug. In this light, the lantern-lit meeting hall of a miner's guild was as much an innovation hub as the machine shop above the shaft. It was where experience was distilled into principle, where individual ingenuity was woven into a durable, collective intelligence. This network of practical learning became the hidden bedrock upon which all the visible machinery was built. But what happens when this concentrated furnace of ideas finally cools, when the last rich vein is exhausted and the pumps fall silent? The legacy of these places holds a final, surprising clue about the true nature of innovation itself. The dark tunnels of the mine and the chaos of the battlefield are closer cousins than they appear. For centuries, the same skills that unlocked wealth from the earth were turned to a far more destructive purpose, creating a powerful, hidden feedback loop that accelerated innovation in both fields. This is the Military-Mining Nexus, a relationship forged in fire and shadow. Consider the ancient art of siege warfare. An army arrives at the towering walls of a defiant city. A direct assault would be suicide. The solution was often found not above ground but below it. Specialized soldiers known as sappers, a term derived from the French word for to dig, would begin their clandestine work. Their mission was to dig a tunnel or sap from their own lines right under the enemy's formidable walls. This was not simple digging. It was precision underground engineering under the most extreme pressure imaginable. The sappers had to calculate the correct angle and depth, shore up the tunnel with timber to prevent collapse, and work in suffocating silence to avoid detection by enemy soldiers listening for the telltale sounds of picks. Their goal was to reach directly beneath a key section of the wall, hollow out a large chamber, fill it with combustibles, and set a fire. The burning supports would collapse the chamber, and with it, the wall above would crumble into a breach. This technique, called mining in a military context, turned geology into a weapon. The counter to this terrifying threat was counter-mining. Defenders, suspecting a tunnel, would frantically dig their own network of intercepting tunnels, aiming to break into the enemy sap and engage in brutal, close-quarters combat in the pitch-black confines underground. This deadly game of cat and mouse beneath the battlefield forced rapid advances in underground acoustics, as each side listened for the enemy, and in defensive timbering to make tunnels more resilient to collapse or attack. The engineering problems were identical to those in a mine: tunnel stability, air supply, and precise navigation. but the timeline was compressed from years into days or weeks, and the penalty for error was not financial loss, but immediate death and defeat. The brutal laboratory of war refined these underground techniques at a breakneck pace, and the knowledge gained by surviving military engineers inevitably flowed back into civilian mining, improving safety and efficiency. Yet the connection runs even deeper than tunnel tactics. Warfare created the single most voracious and consistent market for the miner's product. From the bronze swords of ancient pharaohs to the iron cannons of early modern kings, the engine of war ran on metal. A ruler's power was directly tied to his ability to equip an army, and that required a secure, massive supply of copper, tin, and especially iron. This created a financial cycle of immense power. A monarch needing to arm his forces for a coming conflict would pour money into mining regions, funding new shafts, better smelters, and experimental pumping engines. The demand was constant, and the budgets were often unlimited because the alternative was losing a war. This state-sponsored investment supercharged innovation. The drive to produce more, purer iron for stronger armor and sharper blades pushed metallurgists to perfect blast furnaces and refining techniques. The need for standardized, high-quality metal for thousands of identical musket barrels fostered early concepts of quality control and interchangeable parts. The mine, in feeding the insatiable hunger of the military, found itself funded by the deepest coffers in the land, those of the state itself. It was a perfect, if grim, symbiosis. The mine provided the material means of war, and war provided the urgent necessity and lavish funding that drove the mine to innovate. Each siege dug and each army equipped tightened this bond, ensuring that the technologies of extraction and destruction evolved in lockstep, each pushing the other to dig deeper, move faster, and forge stronger than ever before. The connection between war and mining forged a powerful engine for progress, but to see that engine in its purest form, we must travel to a specific mountain range in the heart of Europe. Here, the abstract principles of pressure, capital, and ingenuity converged into a tangible, centuries-long explosion of innovation. The Erzgebirge, the Ore Mountains, stand as the ultimate case study. In the mid-12th century, prospectors discovered not just surface silver, but immense, deep-lying veins. This was not a simple treasure trove. It was a declaration of war against the mountain itself, a conflict that would demand entirely new technologies to win. The silver was there, but it was imprisoned in waterlogged rock hundreds of feet down. To reach it, the miners of the Erzgebirge had to become masters of three things: moving water, unlocking metal, and governing themselves. Their solutions in each area did not just keep the mines open. They turned the region into a technological powerhouse that would influence the world for over 500 years. The first and most monumental challenge was water. The deep shafts acted like wells, constantly filling with groundwater from the surrounding rock. Bucket brigades were hopeless against this scale. The answer was an audacious network of waterways known as the Kunstgraben. These were not simple ditches. They were meticulously engineered contour canals, sometimes stretching for dozens of miles across rugged terrain. Builders calculated precise, gentle slopes so that mountain streams could be captured and diverted to flow steadily along the hillsides, channeling water to the precise points above the mine shaft. There, the water was unleashed onto massive wooden waterwheels, sometimes arranged in breathtaking cascades, their power converted through complex systems of rods and pumps to drain the depths. This was a landscape-scale machine, a circulatory system built across entire valleys. It represented a staggering leap in hydraulic engineering and civil planning, creating a reliable, renewable power source that ran day and night. The Kunstgraben did more than pump. It powered ore-crushing mills and bellows for smelters, becoming the central power grid for the entire mining district. But even with dry tunnels, the ore presented a second, equally stubborn puzzle. The silver was not pure. It was chemically bonded with copper in a difficult ore called fulleres. Traditional smelting produced a messy, impure alloy. The wealth was locked in a chemical marriage that refused to divorce. For decades, this limited the boom. Then, in the late 15th century, a revolutionary process emerged from the region's smelting huts, the Saigerhütten process. This was a breakthrough in industrial chemistry. Metallurgists discovered that by adding large amounts of lead to the copper-silver ore and roasting it in a multi-stage process, they could separate the metals. The lead would act as a collector, grabbing the silver and leaving the copper behind. It was an intricate, controlled alchemy that required precise temperatures and careful management. The Saigerhütten process turned a previously marginal ore into a bonanza, extending the life of the mines exponentially and establishing the Erzgebirge as the global center of advanced metallurgy. Yet none of this, neither the miles of canals nor the chemical breakthroughs, could have happened without a third, less visible innovation: the law. The scale of investment and the complexity of operations demanded clear rules. Who owned the vein if it crossed under two different farms? How were profits and risks shared among dozens of investors? The answer was codified in a landmark piece of legislation, the Ius Regale Montanorum, or the Royal Mining Law. Established in the 13th century, this legal framework declared that the rights to precious metals belonged to the sovereign, but that they could be leased to anyone who discovered and agreed to work a vein. It created a secure system of claims and royalties, protecting the massive capital investments needed for deep mining. This legal clarity attracted skilled miners from across Europe, offering them rights and a share of the profits. It transformed mining from a speculative gamble into a regulated, professional industry. The law provided the stable foundation upon which the engineering and chemistry could be built. Together, this triad of innovations, the hydraulic network, the chemical process, and the legal code, created a self-reinforcing system of progress. The Kunstgraben made deep mining possible. The Saigerhütten process made it immensely profitable, and the mining law made it sustainable and attractive to talent. For centuries, the Erzgebirge was not just a mining region. It was a university of practical science, a magnet for Europe's best engineers, chemists, and entrepreneurs. Its influence radiated outward as its masters and its technologies were sought after from the Americas to Asia. The story here shows the framework in perfect motion. A harsh environment presented impossible problems. The immense value at stake concentrated capital and minds, and the solutions that emerged from water law to chemical law did not merely extract silver. They built a new kind of knowledge society in the heart of the mountains. Cornwall's story is written in water and fire. While the Erzgebirge mastered water power, the rocky peninsula of Cornwall faced a different geological reality. Its rich lodes of tin and copper plunged deep beneath the water table, and the landscape lacked the powerful, consistent streams needed to drive the massive waterwheel systems of Central Europe. Here, the enemy was not just groundwater, but geography itself. Every attempt to dig deeper was met with a flooding crisis that existing technology could not solve. This impossible constraint made Cornwall the perfect, desperate laboratory for the next great leap in power. The region did not just need a better pump. It needed a new source of force altogether, one that could be summoned anywhere, regardless of rivers or streams. That force was steam. The first practical answer was a monstrous, clanking giant known as the atmospheric engine, invented by Thomas Newcomen, a Cornish ironmonger and lay preacher around 1710. Newcomen was not a distant academic. He was a local craftsman intimately familiar with the miner's plight. His engine was a masterpiece of practical, brute force engineering. It worked on a simple, powerful principle. Steam was injected into a large vertical cylinder, then condensed by a spray of cold water, creating a partial vacuum. The pressure of the outside air, the atmosphere, then pushed a massive piston down with tremendous force. This piston was connected to a great rocking beam, which in turn worked the pumps deep in the mine shaft. It was inefficient, gulping vast quantities of coal to heat the boiler, and its rhythmic sighs and groans could be heard for miles. But it worked. For the first time, a mine could be dewatered by a machine that stood right at the shaft head, independent of the landscape. The Newcomen engine was an immediate, if costly, salvation. Dozens were erected across Cornwall and in Britain's coalfields, where they pumped out flooded mines and allowed extraction to reach previously impossible depths. These engines were not static inventions. They became part of a relentless feedback loop between the mine engineers and the machine makers. The men who operated these beasts under real, punishing conditions became vital sources of data. They reported on weaknesses in the design, on parts that failed under constant strain, and on ways to improve efficiency even slightly. Every saved bushel of coal meant more profit. This constant, on-the-ground feedback created a culture of iterative improvement. It was this culture that a young Scottish instrument maker named James Watt entered in the 1760s. While repairing a model Newcomen engine at the University of Glasgow, Watt was struck by its staggering inefficiency. The entire cylinder had to be heated and cooled with every stroke, wasting most of the steam's energy. His revolutionary improvement was to add a separate condenser. This allowed the cylinder to stay hot while the steam was condensed in a separate, cool chamber. It was a fundamental redesign that dramatically reduced fuel consumption. But Watt's genius did not stop at the drawing board. His partnership with the Birmingham manufacturer Matthew Boulton was crucial, but so was his deep engagement with the mining industry. To refine and promote his engine, Watt spent significant time in Cornwall, the largest market for pumping engines. There, he worked directly with the mine captains, the practical experts who knew the machine's capabilities and failures intimately. These Cornish engineers, like the brilliant but demanding mine manager Richard Trevithick Sr., pushed Watt relentlessly. They demanded higher power, greater reliability, and adaptations for their specific, challenging sites. This pressure from the field was instrumental. It drove Watt to further innovations, such as the double-acting engine, which used steam to push the piston in both directions, and the centrifugal governor, which automatically regulated engine speed. The steam engine was not perfected in an ivory tower. It was forged, tested, and refined in the soot and urgency of Cornish mine yards, where its success was measured in the clear, unyielding metric of feet of water lowered per day. What began as a local solution for a wet rock peninsula became the beating heart of a global transformation. The same basic technology that kept the tin mines dry was soon adapted to drive the machinery of textile mills, to propel ships across oceans, and to power locomotives along iron rails. The Industrial Revolution was, in many ways, sparked by the need to solve a very specific problem, one that had been drowning the hopes of Cornish miners for generations. The engine that changed the world was a direct answer to the mountain's most fundamental question, asked not in words but in the relentless, rising water at the bottom of a dark shaft. Isolation was not a barrier, it was the forge. The most innovative mining districts were often the farthest from the comfortable centers of civilization, perched on rocky coasts, buried in dense forests, or clinging to barren mountain slopes. This seems like a paradox. How could a place cut off from trade routes, universities, and royal courts possibly become a beacon of technological progress? The answer is that remoteness did not slow innovation. It supercharged it by removing the easiest option of all, asking for help. When you cannot import a solution, you are forced to invent your own. This geographical pressure created a powerful culture of radical self-reliance. Every single component of the operation, from the nails in the timber frames to the gears in the pumping engine, had to be sourced, forged, or improvised on site. There was no waiting months for a specialist part to arrive by ship from a distant capital. If a crucial pump rod snapped deep in the mine, The community's own blacksmiths and carpenters had to analyze the break, understand the stress that caused it, and forge a new one, often improving the design in the process to prevent it from happening again. This constant, hands-on cycle of breakdown and repair was a relentless education in materials and mechanics. It turned every artisan in the valley into a practical engineer. The mine's remoteness also meant that any successful innovation had an immediate, dramatic, and visible impact. In a connected city, a slightly better loom might offer a modest gain in textile production, one improvement among many. But in an isolated mining camp, a new method for bracing a tunnel roof did not just improve efficiency. It meant the difference between the mine operating or collapsing, between the community thriving or dispersing into poverty. The stakes were absolute, and the reward for a good idea was not just profit but collective survival. This amplified the value of ingenuity, making the local inventor a true community hero. Furthermore, this isolation fostered the tightest of social bonds. You were not just working alongside your neighbors, you were depending on them for your very life underground. Trust was not a social nicety, it was the foundation of safety. The man next to you in the tunnel had to understand the subtle creak of the timber, recognize the faint change in the air, and know the procedure for a rapid retreat. This shared peril and purpose created an intense, collaborative culture where knowledge was not hoarded by elites, but was a common resource, passed urgently from experienced miners to apprentices. The evening gatherings in the camp tavern were not merely for relaxation. They were vital debriefing sessions where the day's challenges were discussed, solutions were proposed, and hard-won lessons were woven into the community's shared memory. In this crucible of remoteness, the mining settlement became more than a workplace. It became an organism, a single entity focused on a singular struggle against the mountain. This concentration of need, talent, and mutual dependence in one isolated place is what turned geographical hardship into a historical advantage. The mountain enforced a simple, brutal rule: solve it here or fail here. And from that uncompromising demand, some of our most enduring tools for progress were born. The fertile river valleys gave humanity life, but the Rocky Mountains gave it power. To understand why mining regions became such unique engines of invention, we must place them beside their more celebrated counterparts, the great agricultural cradles of civilization. The Nile Valley, the Mesopotamian floodplains, the Indus River Basin, these were the original gardens of human society. Their innovations were profound, but they followed a different rhythm, one dictated by the sun and the soil. The farmers' primary challenges were biological and cyclical. How do you predict the annual flood? This led to advanced astronomy and the creation of precise calendars. How do you maximize the yield from a fixed plot of land? This spurred innovations in irrigation like canals and shadufs, and in biology through the selective breeding of crops and animals. The problems were slow-moving, seasonal, and deeply connected to living systems. Success was measured in the abundance of the harvest, a reward that came months after the labor was done. The pace of change was often generational, a gradual refinement of techniques passed from parent to child. This produced a stable, deeply knowledgeable, but often conservative form of progress, perfectly adapted to the reliable cycles of nature. Now, listen to the rhythm of the mining region. Its challenges were not biological, but physical and immediate. The mountain does not have a season. It presents a constant, unyielding series of mechanical puzzles. How do you move that rock? How do you support that space? How do you separate this metal from that one? The solutions required were not about nurturing life, but about overcoming inert matter. This forced a completely different kind of thinking, one focused on leverage, force, chemical reactions, and structural integrity. While the farmer studied the stars to know when to plant, the miner studied the grain of the rock to know where to place his timber. One was an art of alignment with natural cycles, the other an art of confrontation with physical limits. This fundamental difference in the nature of the problem led to a fundamental difference in the fruit of the labor. Agricultural innovations, while brilliant, were often highly specific to their environment. A complex irrigation system designed for the flat plains of Mesopotamia could not be easily transplanted to the steep slopes of the Andes. The knowledge was deeply local, tied to a specific river, soil, and climate. Mining innovations, by their very nature, were more abstract and transferable. A system of gears that efficiently transmits power from a waterwheel to a pump is a mechanical principle. Once understood, that principle is not bound to the Erzgebirge. It can be adapted to lift water for a town's fountain, to full cloth in a mill, or to saw timber in a forest. The timber framing perfected to hold up a silver mine's roof uses the same geometry of triangles and load-bearing forces needed to build a wider bridge or a taller cathedral spire. The chemical process for separating silver from copper relies on universal properties of heat and affinity, knowledge that could later be applied to refining other metals or even developing new alloys. The technologies born in the mine were toolkits of physical law, not manuals for a specific landscape. They provided a vocabulary of force, material, and structure that could be spoken anywhere a similar physical challenge arose. This is the hidden reason why the remote, harsh mining district could influence the world far beyond its borders. It was not simply exporting silver or tin. It was exporting a new way of solving problems, a mechanical literacy that would become the foundation of the industrial age. The farmer taught us how to live with the earth. The miner taught us how to change it. The furnace of innovation burned with a dark and hungry flame. For all the brilliance it produced, the relentless drive to conquer the mountain exacted a staggering price, one paid not in silver or tin, but in human toil and the very health of the land. The story of these technological crucibles is incomplete without acknowledging their profound shadow. The same pressures that forged new machines also created systems of intense hardship. Deep underground, the work was perilous and unending. Miners faced constant threats from collapsing tunnels, pockets of foul air, and flooding, often with only primitive tools and candlelight for protection. The financial structures that pooled capital for innovation also concentrated power, frequently leading to the exploitation of labor. In many regions, mining relied on systems of indentured servitude, debt bondage, or the labor of those with few other choices, creating communities where wealth flowed upward while risk remained with those at the rock face. Above ground, the environmental footprint was immense and lasting. The demand for timber to shore up miles of tunnels and to fuel countless smelting fires led to widespread deforestation. Entire mountainsides were stripped bare, altering local climates and causing erosion that silted up rivers. The smelting process itself belched smoke laden with lead, arsenic, and other toxins into the air, poisoning the soil and water for generations. The landscape around places like the Erzgebirge or Cornwall still bears the scars, with distinctive, sparse vegetation on old spoil heaps and contaminated streams. Paradoxically, these very costs became new drivers for invention. The critical shortage of timber for fuel, for instance, forced a desperate search for alternatives. This scarcity directly pushed smelters to experiment with coal, a dirtier but more abundant fuel, and to redesign furnaces to use it more efficiently. The need to process ever poorer ores led to more complex chemical methods to extract the last bits of metal, advancing metallurgical science even as it created more toxic waste. Yet not every problem yielded a technological fix. The social tensions born of inequality and dangerous work frequently boiled over into protests, strikes, and unrest as communities pushed back against the conditions that powered progress. And ultimately, the most limiting factor was the earth itself. Every vein, no matter how rich, has an end. regions that had thrived for centuries, whose entire identity was built around the mine, faced eventual depletion. When the ore ran out, the brilliant engines fell silent, the capital moved on, and communities were left to grapple with a stark new reality, often as impoverished as they were before the boom began. This cycle of innovation, exploitation, and exhaustion is the other half of the truth. It reminds us that progress is rarely a clean ascent, but a complex climb with gains and losses etched into the same stone. The mountain's greatest lesson was that no resource lasts forever, not even the pattern it helped create. For centuries, the harsh logic of the mine had dictated the geography of innovation, but that iron grip began to loosen with the very machines the mines had birthed. The steam engine, perfected in the wet darkness of Cornwall, carried within it the seeds of its own liberation. Once this new power source was fully understood, standardized, and made portable, it no longer needed to live at the mine head. It could be installed anywhere there was fuel and a need for work to be done. The technology had outgrown its birthplace. This was the Great Decoupling. The unique, concentrated crucible of the early mining camp, where every problem was immediate and every solution was forged on site, began to give way to a new model. Innovation could now occur in places that had never seen a pickaxe or a timbered shaft. The dedicated Industrial Research Center, the University Engineering Department, the corporate laboratory, these became the new temples of progress. They were places designed for abstract thought and systematic experimentation, deliberately disconnected from the grit, danger, and urgent chaos of the mine face. Engineers no longer needed to be miners. They could study principles in a classroom, draft designs on clean paper, and test prototypes in controlled workshops. The knowledge that had been so hard-won in the mountains was now codified into textbooks, formulas, and standard practices. This was progress, of course, a democratization of inventive potential. But it also meant that the intense, all-encompassing pressure cooker that had forced so many leaps was diffused. The feedback loop between a life-threatening problem and a tangible, field-tested solution grew longer and more indirect. A researcher in Manchester could work on improving boiler efficiency without ever feeling the damp chill of a flooding tunnel or hearing the anxious shouts of men trapped below. The direct, visceral connection between survival and ingenuity was severed. The mine had taught humanity how to innovate under extreme duress, but its final gift was the blueprint to escape those very conditions. The pattern faded not because it failed, but because it succeeded so brilliantly that it made its own harsh necessity obsolete. The story of these harsh, remote places reveals a powerful and enduring blueprint. Mining regions did not stumble into innovation by chance. They became the world's first technological hubs because they created a perfect, self-reinforcing storm of conditions that left no other path forward. It began with the relentless physical confrontation with the earth itself, a daily crisis of water, rock, and air that demanded immediate, tangible solutions. This intense pressure forged a mindset of radical problem-solving where failure had immediate and severe consequences, but pressure alone was not enough. The immense value locked underground acted as a powerful magnet, concentrating the essential ingredients for progress into one hyper-focused space. It drew together a critical mass of diverse expertise, from engineers to metallurgists, forcing their knowledge to collide and combine. It attracted vast pools of capital, willing to fund risky experiments because the potential rewards justified the gamble. And it fostered unique social structures, from guilds that codified hard-won knowledge to legal frameworks that protected investment, creating stable platforms for long-term experimentation. This was not a simple story of necessity as the mother of invention. It was necessity, amplified by concentrated resources and forced collaboration, that fathered entire new fields of engineering, chemistry, and industry. The legacy of these regions is not merely a list of machines they built. They served as the original prototypes for our modern technological ecosystems. Think of Silicon Valley or any contemporary research corridor. The core ingredients are strikingly familiar: a convergence of urgent, high-value problems, a dense concentration of specialized talent, a ready flow of risk-tolerant capital, and a culture that encourages the rapid sharing and testing of ideas. The mining districts of the past were the beta versions of this model, proving that when you gather brilliant minds around a difficult, valuable challenge and give them the means to experiment, breakthroughs are not just possible, they become inevitable. The waterwheel systems of the Erzgebirge were an early power grid. The joint stock companies were early venture capital firms. The Miners' Guild was an early research and development community. The pattern they established, pressure, concentration, collaboration, is a timeless recipe for human invention. So the next time you see a sleek device or use a powerful technology, remember that its lineage may stretch back to a dark, flooded tunnel and a group of determined people who had no choice but to find a better way. The principle they proved still holds true today. True innovation often blooms not in the easiest places, but in the most challenging ones, where necessity is not a vague concept, but a daily, grinding reality. Where do you see this same powerful pattern at work in our world today? What modern challenges are creating their own concentrated crucibles of ingenuity? Share your thoughts below.